So good afternoon, everyone, and welcome to the HortiQD Industry Workshop. I'm Claudio Caramadre from Tinexta Innovation Hub, and I'm very happy to see you all here today because the event we are going to witness is something that matters to all of us, making horticulture smarter, more sustainable, and more efficient. Over the course of the workshop, you'll hear from our partners about new ideas and technology that can really change the way we grow and protect crops. So we'll start with the big picture, obviously. So how quantum dots and SWI imaging can open new opportunities. These technologies used to be too expensive or complicated, but now they are becoming more accessible, and that means that there are possible new applications for agriculture, food quality, recycling, and even environmental monitoring. So we'll also hear about optical filters and how they help us get clearer, more precise images, and about the latest progress in developing new materials for detectors. These are important steps that make advanced sensing not just a research topic, but something farmers and companies can actually use. Then we move to the field. You'll see how spectral analysis can automatically monitor orchards, spotting diseases and pests earlier, so farmers can act faster and reduce the pesticide use that, as you know, it's not something very good. You also discover how robotics and sensing technologies can come together. Imagine a robot, for example, moving through the orchard, checking plant health, and sending data directly to the cloud. That's not science fiction. It's happening today. So finally, we'll talk about data platforms, because technology is only useful when and if we can understand the information it gives us. So by connecting and correlating sensor data, we can uncover patterns and insights that help farmers making a better decision every day. So what ties all this together? It's the vision of HortiQD project to bring affordable, practical, and sustainable solutions to the European horticulture. From cameras to robots, from filters to data platforms. Each piece is part of a bigger puzzle, one where innovation supports farmers, protects the environment, and improves the quality of our food. So I invite you to listen and to share your thoughts, because there will be also a space for this. So just remember that this workshop is not about presentation. It's about building bridges between research, industries, and practice. So thank you very much. And I think we can proceed with the first speaker of today. The first speaker we'll hear from is HortiQD project coordinator Ray Soap. Ray Soap is a senior researcher at Fraunhofer ENAS, specializing in micro and nanosystems for industrial applications. He brings extensive experience in technology transfer and project coordination, ensuring that innovations more effectively can arrive more effectively from lab to market. Is it right, Ray? Okay, so I'm going to share your presentation and leave you the floor. Thanks, Claudio.
Okay. My name is Ray Sauber, as Claudio said, and I am going to present a short intro about the HortiQD project before we dive deeper into the different topics. The project HortiQD stands for Automated Monitoring in Horticulture through Spectral Analysis with Quantum Dot Detectors and High-Resolution Optical Filters. The project runs 36 months until end of 2026. The consortium consists of 12 partners. It's a mixture from scientific and industrial competences, well balanced between. Also, should I? Something? Okay. Between the partners which develop the components and the system and all these things around this, and partners with the agricultural competence and agricultural research, and also the agriculture application of this, or this application of the system. We are 12 partners from 4 different countries, namely Fraunhofer Enas and TU Chemnitz, HTech Group, and BioOps from Germany, Inhort from Poland, SIA, ST, and CTR from France, and Resi, Warrant Hub, Revolra, and Achion from Italy. Some things maybe I can use to mouse. Okay, now it works. Okay, thank you. So what motivates us to starting this project? We address actually 2 agricultural topics. One is the plant health monitoring, the other one is the food quality measurement. And regarding the plant health monitoring, the yield and quality of the apples in our case are strongly affected by diseases, for example, apple scab, and pests, for example, mites. And so early detection is crucial in order to prevent yield losses and to ensure consistent fruit quality and reduce the costs. And it's crucial also for the apply group protection for more precisely and sustainable. But visual inspections are time-consuming and labor-intensive, and many affections are not visible in early stages. So here can hyperspectral imaging help. It combines spectral and spatial information for detailed plant analysis and is able to early, objective, and automatic detected stress, diseases, or pest damage. So the goals here is the reduce of pesticide use in order to promote sustainable food production and the increase of the yield and food quality through timely intervention. Regarding the second topic, the food and quality assessment, we have here also it's also a critical value for the market and for the consumer satisfaction. Key parameters are here: sugar content, starch content, ripeness, texture, color, defects, and size. But traditional quality assessments are often destructive, labor-intensive, and subjective. So here is the challenge that the sampling is quite time-consuming and covers only a small part of the whole harvest, and visual inspection miss subtle defects or internal quality variations, and also continuous monitoring is quite difficult. Here also imaging, or especially hyperspectral imaging, can help to provide, because it can provide non-destructive, rapid, and objective quality assessments. It helps to improve decision-making for harvest timing on the one hand, and optimizing sorting, grading, and storage strategies on the other hand. And it reduced post-harvest losses through early detection of defect and or even ribboning. We are going to address these challenges mentioned before with development of an affordable, easy-to-use machine vision system for precision farming. This consists basically of a new hyperspectral shortwave infrared camera working in the wavelength range within 800 to 2000 nanometer. And core components here are an optical filter able to select the wavelengths, the specific wavelengths with a high spectral and spatial resolution. This is a MEMS-based spectral filter. And another core component combined with this filter is the quantum dot-based detector or image sensor, able to detect the wavelengths until up to 2000 nanometers to affordable price. And this both are combined with image sensing processor or image processor and with an embedded edge processing system. And on this system, the hyperspectral images are analyzed by deep learning algorithm which runs there. And this is used in order to identify correctly this diseases and pests which we are looking for and determine the food quality parameters. And this data are submitted or uploaded to a cloud where data correlation and collection correlation system is running, and combined with GPS data and also data from other sensors like temperature and moisture, you are able to, or we are able to give this information to end user and correlate also this data to give together with a decision support system, the end user also suggestion to use it. And at the end, or last but not least, the overall integration of the system is made by to a handheld device for collection of data by handheld, and to a tractor, to an autonomous tractor system which is able to collect data by autonomous driving through the orchards. Okay, that's all from my side, and now we can move to another speech. Thank you.
Thank you very much, Peter. So our second speaker today will be Andras Patantius Abram from BestQD Solutions. So Andras is the founder of BestQD Solutions, a company pioneering quantum dot technologies for SWIR imaging. And his keynote will explore applications and market opportunities, showing how quantum dots can transform industrial sensing. If you can reach us.
Right, thank you. Skip ahead to my talk. So why would we want to do SWIR imaging with quantum dots? And as a lot of you are becoming more aware, the cost of traditional SWIR sensors made out of single crystal InGaAs is cost prohibitive. And having a lower cost solution is very, very beneficial to opening up new applications. And places like mobile, even industrial applications, machine vision, laser beam profiling, looking at wafers in the fabs, drones for agriculture, health, and leading to personal robotics. All these areas are too cost sensitive and cannot use the traditional sensors. So today, QD-based image sensors have compelling advantages over competing technologies, and the industry maturity is continuously improving, as you'll see. So a bit of history. In 2006 is about where things kicked off. A startup in Canada, Envisage Technologies, started working on lead sulfide quantum dots for RGB and eventually near IR image sensors. And I got the chance to start working there in 2013. And in around 2017, what happened was what I call the mobile boom. Apple acquired Envisage. They were very excited about the prospect of the 940 nanometer performance for mobile. IMEC published a paper on lead sulfide quantum dot image sensors, and a lot of startups became involved. Nanoco, SWIR Vision Systems, Quantum Science, QDI, Quantum Solutions. Everybody started exploiting the performance of quantum dots for image sensors, whereas traditionally they were more established for display technologies. And the next phase, ST Microelectronics was the other big company that became involved directly in 2020. And they published in 2021 a SWIR QD image sensor. And this really demonstrated how mature this technology was for imaging in the SWIR. And Curve, a startup in Spain, was founded. Imberion, which is a Finnish UK company, also announced a QD-based camera. So again, more new companies on the scene. And then now starting 2024, ST Microelectronics paused their development. So it was a sign that the high volume market was not materializing. But at the same time, onsemi acquired SWIR Systems. So another big semiconductor integrated manufacturer became involved. Sony and IMEC both announced papers on SWIR lead-free QD image sensors, showing the importance of lead-free QD. Okay, so what does the ecosystem look like today? Ranges from the companies that supply the QD to the companies that transform that into what I call a liquid semiconductor, the formulation suppliers. There are companies that make the image sensors themselves, and then finally the cameras. And some of the companies operate across the board. Like you see, Quantum Solutions does everything, and they even do drones. You'll see later. And you can also appreciate from this slide the heavy European activity in this area. So, and I'm not including the UK companies. All the QD suppliers in this slide are in the UK. So yeah, a lot of EU activity, and a lot of sources of good QD-based image sensors today. Though what distinguishes most of these participants in the market today is that they're low volume. So ST Micro is paused. Sony is in the R&D phase, as we'll discuss. They're not producing yet into the market. So all of these are small volume, and they have to invest in scaling up to supply the market better. Okay, a little bit of basics about how these photo detectors work. With displays, you get light out from the quantum dots. With the photodetectors, you send your photons in, and you have to extract the charges. And the big implication for this is that you cannot put a thick passivating shell around the core of the quantum dots, which is what is used in display technologies. So the passivation is thin, and you really work hard on the quality of this thin passivation to allow good charge transport. So your electron can go to your ETL, your electron transport layer. Your hole gets to your hole transport layer. And again, the quantum dots in this case act like a liquid spin-on semiconductor. It's really crucial to have a high purity, high quality material for this to succeed. On the right, you see the cross-section of what a ST Micro published in 2021. This is what an image sensor would look like for a mobile application with pixels are pretty small. You've got microlens, anti-reflection coating. The actual photodiode is the quantum film here, and then the copper connections to the transistors of the readout circuit. And when you're working with your quantum dot image sensor, of course, it's critical to understand your application and the metrics that really matter. And often comes down to signal to noise. And so you have to make sure that it's high enough. So your QE, your quantum efficiency is important. How many photons hit your pixels is important. Your exposure time. Larger pixels help. And you want to keep your dark current down and your read noise down. But resolution is also critical for a lot of applications. Maybe a bit less for HortiQD, but a lot of cases you're trying to distinguish small features for authentication. This is important. So small pixels really help. Pixel count really helps, and you want to keep your crosstalk down. And finally, cost is always a factor. So your readout cost, the cost of adding your photodiode to the readout is important. And then to complete the system, your camera, your optics, and your illumination source. depending which wavelength you operate at, or if you're doing broadband system, your illuminator may be a big part of the cost. Okay, so keeping all that in mind, for mobile applications, you end up with pretty small pixels. Below 5 microns is typical, so you get high resolution in a small package, and it's a very cost-constrained and power-constrained application. Automotive is also cost-sensitive, but less so, and they can tolerate bigger packages, bigger pixels, but they've also trended towards 2 to 3 micron pixels for driver monitoring, like 2 to 6 micron pixels for collision avoidance. And then other applications like agriculture, like we're discussing here, typically end up with larger pixels to get more light sensitivity. And when you have a bigger pixel, you can put more transistors in, you have a lot more functionality you can do. And always you have to optimize signal-to-noise resolution and cost. All right, so let's look at the competing technologies and compare them with the quantum dot approach. So the strength of quantum dots is achieving really decent QE, like 40 to 60% has been published, and even higher. They can do a very small global shutter pixel, as STMicroelectronics has demonstrated. The dark current is well below microamp per centimeter squared, so it's quite good, and I'll show you a comparison with the other technologies. And low cost, below $10 die is possible in volume. And a wide spectral range is also very, very attractive. The weaknesses, I would say, that for the existing players, given that STMicroelectronics has paused, reliability is not demonstrated yet, so they're working on that. And they all need to invest to scale up their production and meet the new demand that is coming. Compared to low-cost InGaAs, InGaAs is more expensive, and the dark current's not that great. It's pretty new technology, but it's hard to make low-cost InGaAs with low dark current. Germanium and silicon has been around for a long time. Tri-Eye, Ardilux have been working on it. The QE is kind of similar to quantum dots, but the cost is higher. They're trying to finish their reliability work this year. Dark current's really bad. It's intrinsic to germanium, unfortunately, and the pixel size is also bigger. And organics is always around, and they can be low cost, but the QE is not that great in the sphere. Dark current's also a bit high, I would say, and their stability is also in question. So overall, QD are positioned to be the best possible technology for low-cost sphere imaging. And so dark current is a critical metric for these kinds of sensors. And if your dark current's too high, you're going to fill up your pixel with just noise. So you can work around with that by using strong illumination and short integration times, but then that's cost and maybe eye safety considerations if you're using lasers. So it's important to bring this down. And over time, the industry has advanced a lot here. And you see on this chart 3.5 quantum dots that are lead-free and lead sulfide quantum dots. And overall, lead sulfide is better. The fact that the dark current goes up as the wavelength gets longer is normal. That's just a scaling of the thermal generation. You see 3.5 lead-free QD still need to improve by an order of magnitude to catch up with lead sulfide QD, and this is important. And so, for example, Sony published some work last year where the dark current's the blue dot, 10 to the minus 1e minus 4 amps per centimeter squared. Pointer, wow, it's very high, but they've since improved by 2 orders of magnitude. They've told me unofficially. So it's getting there, and you can see where low-cost InGaAs and germanium and silicon are positioned. They're high, and that is limiting for a lot of applications. Like eye safety is a big concern in the sphere. Okay, so let's see who the suppliers are. Inoko is one of the leading suppliers. They're very good at lead sulfide and indium arsenide and other 3.5 quantum dots. They provide a big range, a very strong IP. And they're the only ones who have supplied a 300 millimeter fab, because they were the supplier for STMicro for lead sulfide. So a lot of experience with supplying electronic quality quantum dots. Quantum Science is also in the UK, and they're brought up a lot of good products, both lead containing and lead free. And they also supply inks, which are useful for like one-step coding. So yeah, good, relatively a new player, but shipping some good quantum dots. Now, if you look at the sensor suppliers, Sphere Vision Systems, actually they go all the way to the camera, and they're in the US. They have a very innovative range of products, and they were, the first, officially the first ones with a QD camera on the market, 2018. And they have offerings that are sensitive out to 2 microns. They've started to work on reliability, which is a good sign. But they're trying to make money from the lower volume industrial, scientific, and defense markets. And yeah, big range of products, very innovative. Even like they have a handheld one, Accurus Go, which is great. Emberion has also been around for some time, and they have very high quality polished product, sensitive out to 2 microns, like Sphere Vision, and they continue pushing the longer wavelengths, and so up to 2.5 micron with QD, and they're pushing to have a super pixel which combines visible, SWIR, and thermal imaging even in one sensor. So very innovative company, and these are buy good cameras from them today. QDI Systems is in the Netherlands. They have very strong experience with ink, so one-step deposition process, which they optimize first for X-ray products. So that's one of their product lines. You can do very good X-ray imaging with quantum dots. And they have a really high-performance QE and dark current for their QD-based SWIR sensor. And they've recently shown up performance up to 2.3 microns. And they're in the process of scaling up to wafer level processing this year. So it's very, very exciting. They're growing quickly. Quantum Solutions in the UK, as I said, has offerings across the board, from QDs to cameras to drone-mounted cameras. So it's it's very exciting. So they've gone for more vertical integration, and I'll show some examples of what these drone cameras are optimized for. They're application specific. So solar panel inspection, water is for agricultural applications. It's very innovative and opening up new markets. So this is what they published with their solar panel inspection system. So they go, you can get all the data, you see it, you can see it live. It classifies the defects and provides a report. It's fully integrated, very, very nice system. And for moisture analysis, they again provide a live image of moisture content, and this is what you want. This is what enables farmers to make smart decisions. Curve is based in Barcelona, so they I think are actually quite advanced. They've been a bit less vocal about their capabilities, so hopefully you see some products coming out soon from them. They are working on their wafer level capability and trying to bring that up this coming year. So that's a sign that they're happy with their performance, and they're investing in scaling up their production. So yeah, it'll be very interesting to see what they come out with in terms of products. STMicro, okay, as I said, they paused their development. They had really good QE at 1360 nanometer, and some of the best dark current in the industry at 23 nanoamps per centimeter squared. Yeah, really good global shutter pixel, really high resolution, good photo response, non-uniformity. this, well, it was a great honor to be part of this work. Maybe it will come to the market one day, but for now it's paused. Sony is the other big player now who's working hard on bringing QD imagers to the market. So they probably will industrialize in 2027. Their R&D team is working hard on performance and reliability. And they showed a year ago at IDM their wafer level processing. So they have the capability, they can get images, and they keep improving. As I said earlier, the dark current is a big factor that you want to improve on. Interestingly, there's targeting, of course, the cost-sensitive markets like agriculture, but they're also hoping for mobile applications to come back, and we'll talk about the markets. And here's what their performance looked like last year. So they published a near-IR version, 940. That's the first line. Pretty decent quantum efficiency, about 40% at the peak. The dark current was pretty good too. Their SWIR performance, which is the bottom line, the dark current was much higher, and the quantum efficiency in the SWIR was kind of below 20% and down to 10% at 1450. So not so high performance there, but I think they're making a lot of progress internally. IMEC is the other big European entity, and they've done a lot of work with quantum dot image sensors. Of course, you all know how they work. They need a good partner to continue the industrialization program with, but they have really good facilities and a readout circuit for quantum dots. So a really good place to partner with for industrial R&D. Okay, so let's look at how the markets are shaping up. So we have today's low volume markets, the industrial, like laser beam profiling, industrial machine vision, wafer inspection, the drones, as we've seen. The emerging volume opportunities could be in automotive, collision avoidance and driver monitoring. There's a lot of interest for this because the existing solutions have limitations. And the longer term, the potential high volume opportunities in mobile, health, personal robotics, and maybe also display-based sensing. So low volume markets, as we said, are being addressed today. So Emberion, Quantum Solutions, QDI, they're going after these, they're offering solutions, and you can make good money by offering these people some cameras based on quantum dots. But more could open up for sure if you keep lowering the cost. And once these companies scale up to wafer level processing, they'll be able to do that. The mobile interest in QD-based sensing is, I would say, at a minimum right now for sure. 940 was a strong interest, as I mentioned, in 2017 to 2019. But still, it's hard to compete with silicon. There's some interest in under-display SWIR sensing, but then the display changed, so that opportunity went away. This application is staying at 940 nanometer for now. Could there be a future opportunity? Maybe. Maybe if there's like a health application that comes out. There's some specific reasons why authentication might go, say, 1130 nanometers due to screen reliability. If they're trying to put the emitter for the Face ID module under the screen, then that causes reliability issues, and potentially it could happen. But it's in the future. Automotive, I think, is, again, the best application for now that could materialize. Collision avoidance and driver monitoring to make sure that the driver stays awake. SWIR has big advantages over near IR. The better eye safety and the lower solar background at 1130 nanometers is compelling. And quantum dot imagers could win this opportunity. Because of their lower dark current and also small pixels. Health is another area where SWIR imaging has a lot of benefits. It's a market with more barriers, but there's a lot of areas where SWIR imaging could be used. So we know that QDI is targeting the X-ray market, and QD could leverage high resolution and small form factor to penetrate these markets. And I think once these companies that are active today have more offerings, there'll be more interest in this area and more applications opening up. Agriculture, okay, as we've heard today, a lot of opportunities for using SWIR, so moisture detection, disease detection, nutrient monitoring, harvest timing, weed versus crop differentiation. Okay, so there's a lot. QD-based solution makes a lot of sense here. And QD, as we saw from the drone-based solution, they're already capturing some of these. So to get more volume here, you really need wafer level processing to be developed, and that's in progress with a lot of players. And going to longer wavelengths will always be helpful to get more information via the hyperspectral approach. So where we are in conclusion, there's the path ahead is for a lot of these companies to push to capture the automotive opportunity. I think if you put a good sensor in the hands of the car makers, they will be very interested. There's a good opportunity in the low volume applications that are being exploited today. You want to keep growing those, make a lot of money selling cameras and sensors, and then keep improving performance to enable new applications. Health, mobile, maybe personal robotics. So QD image sensors are now established as a platform technology, a very active industry, and it's going to keep growing. Thank you.
Okay, thank you, Andras. So I think that we can proceed with the next one. The next one is actually Carla Hiller from Fraunhofer Hennas. Carla Hiller is a scientist at Fraunhofer Hennas with expertise in optical systems and filter design. She focuses on translating advanced optical concepts into practical solutions for imaging and sensing technologies. Carla, I think you are able to share your screen. I'll just...
It should be already done. Can you see something?
Yes, we can see it. Thank you very much.
Okay, then I would like to start. Welcome, everyone. Here today, I'm representing two organizations in this HortiQD project, both Fraunhofer Hennas and Chemnitz University. And this talk is about the optical filters. So how come these optical filters now into this concept for HortiQD? Rai already showed this shortly. I put this picture here again. So we have the light, the incoming light from the objects we want to check, and the filter, the light will pass our filter. And this will be a narrow band filter. Only a few wavelengths can pass this filter and reach the detector. So we can take pictures with different wavelengths, and hereby can extract additional information about our plants we would like to analyze. And I will concentrate in my presentation on this filter. So what do we need for such a filter which works in transmission? We need two reflector carriers which are parallel to each other, and we need optical reflectors which allow that only light with specific wavelengths which fulfills this condition of constructive interference can pass the filter. And this depends on the distance between the reflector carriers and the order of the filter M. And now, if we arrange this so that one of these reflector carriers is movable. Then we can change the distance, and hereby we can change the transmission wavelengths. And so we can get this filter tunable. So we can analyze different wavelengths with the same filter. Important parameters are this transmission wavelength, so how much transmittance we get, and then the so-called free spectral range. You see, this is a periodic signal, and only in this range in between two peaks we can work with our filter to have the result which we need. And also the bandwidth is important. So we want to have a small bandwidth to have a high resolution regarding the spectral range. So this is the basic principle. The reflectivity of these reflectors, for this we use, for instance, distributed Bragg reflectors with the product of the refractive index and the thickness equals to quarter of the wavelength of our filter, and we would like to have materials with high reflective index contrast to build up such stacks. So about the movable part, so how can we get the motion in our filter? Electrostatic drive and capacitive detection is very interesting for the MEMS. So it's very easy arrangement. We just need a silicon spring, for instance, a movable part. We attach one electrode to this part, the other part is fixed, and now we can change the distance here. And this works in two directions. Either we can sense, so if the distance changes, we see a change in capacitance, or we can apply a voltage and create electrostatic forces, and hereby we can move one of the plates. So how does this look for such a filter? To translate this in a filter construction, this is a schematic cross-section of such a filter built of two silicon wafers in this case. If we work in the infrared range, silicon is transparent. So we have here our springs, we have here our optical reflectors, and here the electrodes. And if we apply the voltage, you see this here, we can control the transmittance of the filters. So this is a long-term development together with the company Infratec in Dresden. They have their own pyroelectric detectors, which are combined with this filter. And we can use this, for instance, for gas analysis, because gas has characteristic absorption. And this information can be read out when we tune the filter over a certain wavelength range. So here you see one example for this from our latest development. In this case, we have two movable reflector carriers. We work in the near infrared range. We have specific distributed Bragg reflector materials. And yeah, with this approach, this shows just some values what we have reached with these latest generation filters, which are very small, only 5 by 5 millimeter size, with a large optical aperture of 2 by 2 millimeter. So this is just one wavelength range we can work in. And you see some parameters with a relative low activation voltage and also good bandwidth and good maximum transmission. So this is the working range of these filters in this case. Yeah, and as I already said, it could be used, for instance, for gas sensing. On the other hand side, we also looked for filters in the visible range. Here we cannot use silicon as reflector carrier because the silicon is not transparent. So we switched to a concept based on a glass substrate. Again, a silicon upper wafer which carries a reflector. In this case, it's a membrane-based reflector carrier. And we put the electrodes for electrostatic drive directly on the membrane. And we tried different approaches for the reflectors. Again, in this example, we have chosen Bragg reflector layers made out of silicon nitride and silicon oxide in this case. And you see here a photo of this filter. And also for this specific application, we had the goal to have very narrow band filter, very small bandwidth, only a few nanometer. And for this, we had to use higher interference orders, which makes the free spectral range very small. But nevertheless, also with this approach, we could create prototypes and have this available for applications. But now for the project HortiQD, we target the wavelength range in between. So it's from approximately 0.8 to 2 micrometer is our target range here. So this means we had to look at first for new distributed Bragg refractor layer stacks. So we tried some silver-based stacks at the beginning, which works good in the visible range, but not so much in this near-infrared range. And our previous polysilicon-based stack are not cannot be applied on glass substrate because the deposition temperature is too high. So we ended up, or we developed new amorphous silicon-based reflector stacks, which can be deposited with a low PE CVD, low temperature PE CVD, together with silicon dioxide reflectors materials. And so we arranged this at first in such so-called étalons, which are not movable, in order to try the optical properties of these new stacks. So this is a schematic cross-section. We built different gaps in between, and with this we measured the transmittance of such filters. So first group with this layer stack, which you see here, work in the range of 0.8 to 1.1 micrometer. And we put different cavity sizes, so we see different wavelengths where the transmittance is visible. And this was meant to build a second order filters, so that cavity size is nearly the transmittance wavelengths. So we have a lot of such filters with different cavities available now, also for the higher order wavelength range, 1.1 to 1.7 micrometer. We arranged the thicknesses accordingly, and also we built up different cavity sizes. And you see here the responding filter characteristics. Also, we see the free spectral range. Here in these examples, we see some inhomogeneity over the wafer. This means the cavity size is not fully equal for the different samples. That's why the values are a little bit varying. So, but now the task is to build up the movable filters over the whole wavelength range. And for this, we did new designs based on glass silicon compounds. And the main idea was again to go to membrane-based reflector carriers, which are held in a silicon upper substrate with springs. And again, we find our electrodes to drive the whole thing. And here the green element is this optical layer stack. So this is very complex, and it's also challenging to maintain these whole large optical area with the membranes, to make the membrane stable enough, flat enough. And that's why this is not the only approach we are following. We also tried a second approach where we embed a thicker glass material into a silicon wafer. And then we use our optical layer stack again So it's the second variant. And the third variant for the higher wavelength range, above 1.1 micrometer, we also tried a silicon compound where this is still the reflector carrier, and the lower wafer is still a glass reflector carrier. And with all these three variants, we are underway now in this project. And yeah, you can imagine this is a lot of work to be done. It's not all finished, so the goal is to have at least for variant 1 and variant 3 samples available till end of the year. Presently, we have first results to this approach. This I can also show you here on this slide. So we did the first wafer compounds, and we also could do some first optical transmission measurements. So here we find our transmission peaks of interest. Also, what you see is there's a variation also in the peak transmission and in the bandwidth. So more of these bonds will follow, and hopefully we can get some further results also for the electrostatic tuning. And we are then able at the end of the year to supply first such tunable filters for the build-up of the system together with the detectors. So yeah, for a short summary at this point, so we think that such tunable filters are very promising components, both for the spectrometry, as we have already demonstrated for the gas spectrometers, but also the new topic for us, the hyperspectral imaging. So in this wavelength range, we have well-established technologies already. We have also proof of concept for the visible range, and now we want to fill the gap between these ranges with the new class of filters. We want to enlarge the optical area to adapt it to the detector area. But we find that the integration technology is challenging, more challenging than expected. So we have first results at the moment, but much more results will follow in the project. Thank you so much for the attention.
Thank you very much, Carla. So I think we can proceed with the next speaker. The next speaker is Peter Reis from CA. Peter Reis is a leading researcher at CA, internationally recognized for his work on quantum dots and nanomaterials. His talk will highlight synthesis and properties of quantum dots for sweep detection, bridging fundamental science with applied innovation. Is it right, Peter? Yes? Perfect. So let me first of all share your presentation.
Yeah, good afternoon. So we had industrial landscape with Andras. I will focus more on the quantum dots and more from academic point of view, of course. Let me see. I skipped that, of course. Not so much of an introduction. So we have seen the advantages of quantum dots, which are mainly related to the lowering the cost for 3D imaging. There are many challenges. Most of them are related to the transport in quantum dots thin films and maybe the stability on the operation. We have seen a couple of established applications where they could have high interest and also emerging ones. So as Andras mentioned, probably automotive will be a very good one. And we should keep an eye that in the mind also that quantum dots are not only good for imaging, but also for illumination, because you can have very good first sense quantum yields there. So they could be active light sources for different applications like time of flight or structured light or LiDAR. And you can place, of course, the emission of the quantum dots in the dips of the solar spectrum by tuning the size or tuning the material. So this gives also the opportunities to have quantum dots emitters and sensors. So with same materials. Speaking about materials of interest to go in the sphere range, there are many of them summarized in this review paper. A couple are missing, but so we focus on lead sulfide, I would say, which is the first generation major material for sphere imaging and emission. And the second generation would be RoHS compliant 3.5 materials like indium arsenide and indium antimonide. And there's a few new materials coming up. I go in the very end to them. So lead sulfide has been for a long time the workhorse for QD photo detection with many industrial players, already mentioned by Anders before. So I will not go in the details. You have some specs of these materials. And we had a collaboration with the guys from ST on the subject. So, and at the time, we looked a little bit at the synthesis and we wanted to get rid of this very evil smelling sildated precursor and using these thioureas as the precursors for the synthesis. And actually the advantage is you can very easily tune the size just by changing the substituent of these molecules, of these sulfur precursors, and you can have very decent absorption spectra, as you can see with the very sharp absorption peaks there. And in the next step, so we wanted to automatize the synthesis using a continuous flow system with the advantages to have a higher reproducibility, a scalability, and also in these tubular reactors, you have very good mass and heat transfer. And actually that can work. So here you have the flow diagram. So you can use it for both the core lead sulfide QDs and the core shell with a cat sulfide shell. And so we could scale up the synthesis to here, for example, 3 grams in 90 minutes, so which is pretty fast. And we could get very high quantum yields of around 90% for 940 nanometer emission with lead sulfide, cadmium sulfide. And also on a side note, we can use the same approach, so this flow synthesis also for 3.5. So we started with indium phosphide, which is of course invisible and not in the sphere, but it's easier to start with indium phosphide. And you can use it also for indium phosphide zinc sulfide, and this can be done in a very cost effective way and in a very reproducible way. You can get highly emissive QDs in using this method. Concerning lead sulfide, so you can adjust, of course, the emission there to be at the right wavelength in the solar dips, as you can see here. So that's working quite well. So now going to these lead-free materials, so RoHS compliant materials. So here you can see there are several materials which could be in the good range. So you can see here the size dependence of the band gap. And if you want to be in the 1 to 2 micrometer range, so you can use different materials like indium arsenide, indium antimonide, for example, there. But there have been some simulations done by Bilal Shehabou and Christophe Delrue to look also at the absorption of these layers. And so, of course, they used some models. For example, they looked for a thin film of QDs with small ligands, EDT ligands between them, and a packing fraction like that. But what we can see clearly from this diagram is that with lead sulfide and lead selenide, so you have a much higher absorption coefficient, which means in turn, if you go to indium arsenide or indium antimonide, you would need to get to use much thicker films to get the same absorption, which makes it a little bit more challenging. On the other hand, what has been seen also is that you should get a much faster response time than with lead sulfide due to lower permittivity. So now concerning synthesis, so it's in one phrase, it's much more difficult to make the 3.5s than lead sulfide. For that reason, also there is less work on that, and the size distributions are less good. So that comes from the fact that they are much more covalent than the lead chalcogenides, and so which means that you need harsher reaction conditions. You don't have the same type of growth, and also you have very few suitable group 5 precursors, so which makes it much more challenging. So in our case, we are developing synthesis based on safe and economic amino arsine for indium arsenide quantum dots, and in combination with indium 1 halides. So here you can see we can easily tune the size and the absorption spectra by just temperature control. So all of our work, we don't use any size selective precipitation. So they're quite uniform, and we can cover a range of 700 to 1300 nanometers. In the literature, so because I will also give some results of literature, of course, there's a recent report from this year from a group in Hamburg, Jan Nielhaus and Ulf Meth. So they could grow indium arsenide very big, so up to 40 nanometers, which is really a record value, I would say. And you can see also the absorption goes very far. So they couldn't even measure how far it gets, but it's for sure more than 2.5 micron or even 3 microns. So that's really an interesting result, I would say. So it's based on using small indium arsenide clusters, which are produced in the first stage and then grow them bigger. Also on the photodetector side, there has been some work. So that's from the group of Soe Jiong. So they made some calculation to check what would improve the efficiency as a function of the layer thickness. And they found out, okay, that there are some good ranges, and they could tune the thickness. They could make it bigger by tuning the solvent used for the ink preparation, and they could go up to an EQE of around 80% at 940, so which is also a very good value for indium arsenide. And then coming to the indium arsenide integration on silicon, so we have already seen the results from Sony and IMEC presented by Andras. And we did it also in the HortiQD project together with Bérangère and her team at Leti. And actually, we are at state of the art, I would say, at 1,100 nanometers. We have measured an EQE of 38%, and with a dark current of 5 to 10 to the minus 5 ampere per square centimeter. So which is in the same ballpark as these reported results from other teams. 1 minute on the core shells. So you can use them also as emitters. So in our case, we grow indium phosphide zinc sulfide shell on the surface. We got PL quantum yield up to 85% with indium arsenide at around 1000 nanometers here. At IIT, in the team of Liberato Manna and Luca Di Trisio, they use very thick zinc selenide shells there, 7 monolayers. They also get high quantum yields. And then at Westlake, Botois Cheese Group, they got virtually 100% of quantum yield with this very thick intermediate zinc selenide shell, so with a triple shell on indium arsenide. So going further to the sphere range, you could use indium antimonide because for the same size you have longer wavelengths there. That's just an overview of the different synthesis methods reported. And you can see that it's been really focused in the last 5 years. So many of them came out in the last 5 years. People are generally going away from the pyrophoric silylated antimony precursors to antimony halide or aminostibine. And then you need to use reducing agents, which could impact the reproducibility and scalability. And once again, in our case, so the red line, we are leveraging the indium 1 precursor chemistry to use the indium precursor to reduce the antimony precursor. And one other key aspect in our synthesis is that we have to mix both precursors, so you can see the comparison, otherwise it doesn't work. And we can have a decent tunability of the absorption spectra. Once again, it's not size selected there. Of course, you can make it better when you do size selective precipitation. In the literature, so you can see that people were able to grow indium antimonide also bigger. So that's one report on 16 nanometer sized indium antimonide, which goes out to more than 4 microns in absorption. That's also very recent work. So, and the surface treatment was done by HCl, so with a strong acid to remove the oxide on the surface there. They got really decent hole mobilities and could integrate it in this kind of photoconductor, which is working in the mid-infrared infrared range. You have also photodiodes, of course, based on indium antimonide. So that's the work from Ted Sargent's group here. You can see with an EQE of around 33% at 1388 nanometers there, with a dark current 14 microamperes. And there's another one from Gerasimos Konstantato's group. So there they use indium antimonide, indium phosphide core shells to better passivate the surface of the indium antimonide. So that's very emerging. You can see all these works have come out in this year, and there are also alternative materials. So that's my very last example. So silver telluride has come up. So that's also, you can see, you can have very nice absorption features there, and you can tune it till around 2 microns also. And there has been the demonstration also of a decent photodiode, once again by a group of Gerasimos at ICFO. And also another remarkable detail about that one is the air stability. So the detector has been produced at open air. So that's also something interesting. So with this, I would like to conclude. So we have seen that it gives you the largest wavelength coverage, is most major. If you go to the 3.5s, you can have a faster response time, but the synthesis is much more challenging. Indium arsenide can be grown quite big, so eventually it can be used to hold for the whole sphere range. On the other hand, these big particles, how good are they processable? That's another question, of course. Indium antimonide is more sensitive to oxidation, could go for longer wavelengths for the same size. For the moment, the performance is a little bit lower than with indium arsenide, but it's increasing, it's improving. The toxicity between both has to be studied. So indium arsenide versus indium antimonide. This will be done at CEA, by the way, next year. And then alternative materials like silver telluride are emerging. There could also be some issues there about this silver mobility in the thin films and the self-doping and stuff like that. But that's still an interesting approach to follow. And for all these materials, of course, there's still many challenges in terms of ink preparation, stack optimization, and thermal stability. So there's still a lot of work to be done. So with this, I would like to thank my team, our collaborators, and our funders, and you for your attention.
Thank you very much, Peter. So we can, I think, go on with the next speaker before the short break. The next one is Mario Schenker. He represents H-Tech company, a company dedicated to making SWIR imaging affordable and scalable. He will present how quantum dot-enabled cameras can unlock new horizons in imaging, moving from high cost to high impact. Mario, I think you can actually share the screen, right?
I can, yeah. Let's have a little try. Okay. So you probably see yourself in selfie mode right now?
Yes.
Okay. All right. All right. I hope everyone can understand me clearly. And just 1 second, please. I hope everyone can understand me clearly. And yes, thank you very much. Dear ladies and gentlemen, The following slides will provide some general information about Sphere technology and the Sphere camera we are building in the project right now. My name is Mario Schenker, and I'm responsible for sales and customer support at the HTech Optronic and Sensor Solutions, a part of the HTech group. As mentioned before, we are a company that specializes in manufacturing of digital camera, video management, and display systems according to customer requirements. I'm replacing today our head of hardware department, Mr. Christopher Hofheinz, who unfortunately cannot be here today. So I have to mention I'm basically a little bit sporadic involved in the project, but I will do my best to answer your questions. Otherwise, you are welcome to send me a mail with your request, and I will forward this to the respective colleague that you receive a specific answer. And with that out of the way, let's get into it. Like Andras pointed out, the typical application fields for Sphere technology lie in biochemistry, security, especially this sector is really growing right now, agricultural industries, as well as spectroscopy and material analysis. I will show some examples on my next slide, but a significant fact for Sphere technology is that the sensors are sensitive to wavelengths of light out of the human visible range. As you can read here, human eye can realize wavelengths of light between 380 and 780 nanometers, and Sphere technology is capable to provide a visibility of wavelengths up to 1700 nanometers if we talk about the shortwave infrared area. You can see these ranges down here on the scale, and at the bottom of the slide, that visible light in the middle is the range we all are capable to see. With longer wavelengths to the right, we move into the infrared range. Within the picture, we can also see some examples of sensors on the market that are specialized for these wavelengths areas. For example, the IMX series up from 990 to 993 from Sony. So why we use this kind of technology and what benefits comes out of it? Our surroundings behave and appear different in higher wavelengths ranges. Some might be darker, or some things may be almost invisible, and this gives us the chance to analyze material and detect aspects that we cannot see with our own eyes. For example, on the left, the apple with an infrared camera. Here on the right, this is a sphere image. We are capable to see the pressure damage in the apple. That gives us the chance to determine an economically better choice for the fruit itself. For example, in an agricultural context, it might be better to use this piece for juice instead of sale in the market. On the picture in the middle, you can see on the left half some rice with little stones within the visible range for humans. The right half is a sphere image where we can clearly separate the stones from the rice because the rice is displayed differently in sphere range. This example shows that sphere technology also enables us to check large quantities of materials of impurities. And one last interesting fact to know is sphere technology is used to detect counterfeits in art. As I mentioned, some materials are basically invisible within the infrared range, and this seems to appear to all colors as well. So if you direct a sphere camera to a painting, like here on this picture on the right, you might be supposed to see the concept drawings from the artist he drew with a pencil. So if you stare on an empty wall, you know it's not a real. You're not looking at the original. As in here, we're talking about a very useful technology, but as our
Mario.
Yeah.
Sorry, I think our audience is saying that we not everyone can see the slides. So I don't know if you want.
Just 1 second.
Try to see. Yes, at least share again the screen. You can also give us feedback on the audience side. I mean, if you want to let us know if you can see the slides or not.
So 1 second, please.
Yes.
So one thing, and
Okay, we have positive feedbacks. Mario, sorry for the interruption. Please go on.
Yeah, absolutely no problem. You guys want me to go back one slide before?
No, you can continue. Thank you.
I can continue. Okay. So where have I been? Yes. One more thing. Yes, as we seen on the slide before, as long as you were able to see it, we are talking about a very useful technology. And as our partners mentioned before, today's weird technology, unfortunately, comes around with two aspects you have to consider. Most sensors are made of indium gallium arsenide, a common material used in chip technology. These sensors usually do require a thermoelectric or active cooling to provide good performance on high exposure, and they are usually pretty expensive. Yeah? For one piece, you can assume about, let's say, $6,000 upwards, depending on manufacturing or specifics that you need. The quantum dot technology that will be used within this project will not entail these disadvantages. We will reach lower cost, and there will be no need for an active cooling. The camera as will be built up, or let's say divided in two parts. We will have a front and a back end that will contain specific, which each will contain specific boards for the functionality. The front will be developed for the optics with filters and sensor, the back for the electronic and data processing. This dividing makes the whole system more flexible towards modifications. If there is a change in one of the parts that has to be done, we do not need to re-engineer the whole system. And I also have some specification stats that might be also of interest here. As I mentioned, the modular concept, as I have shown on the slide before, that divides optic and electronic. The camera also will be able to operate within -40 till 85 degrees, which is necessary in agricultural use. The communication interface will be a regular 100 base TX connector, and a power supply of 54 volt will be needed. As you can guess, these small dimensions, so the camera will not take too much space, and the lenses with a regular C-mount connector can also be adapted. The spectral range will be set within 900 to 1700 nanometers, and the video encoding standard will be H.264. Yeah, basically, this was these were my slides. I hope I was able to provide some useful information, and I thank you for your attention.
Thank you very much, Mario.
Oh.
So right now we have a short break, and then we will be back with session 2. So this short break will take 10 minutes. So see you all again at 3:30. So starting from now. Okay? Thank you, everyone. See you in 10 minutes. Okay. Hello, everyone. Welcome back. Give you another, let's say, another minute. In the meantime, I will present the next speaker. The next speaker is Joanna Łapska from HortiQD. Joanna is a researcher at the Institute of Horticulture in Poland. She works on spectral analysis and orchard monitoring, developing tools that support more sustainable horticultural production. So, I will share your presentation, Joanna. Okay. No, sorry. You're right. Let's start. Another second of patience. All right.
Thank you, Claudio. Good afternoon. let's move a bit to the more agriculture part of our HortiQD project. Okay. Plant production, why it's so important? Plant production is the base for the plant-based food, which is very important for ensuring food security, not only for humans, but only for the animals who are also consist the food for human. And also we know that plant-based food is rich of many components which are very good for the human health. What is also known that the damage of the crop production due to pests, diseases, and weeds can reach even 40% per year. So it can be translated into money over 200 billion US dollars each year. So application, the base of the plant protection is application of the chemical plant protection products. However, from one side, on the one hand, it ensures production efficiency. However, on the other hand, it's a threat to the human health and the environment. So what can be the solution? The solution can be integrated pest management, which is already obligatory in the European Union for years. And integrated plant protection production involves integration of various different plant production methods with a priority given to non-chemical methods. And non-chemical plant protection should be supplemented with the use of pesticides only when the expected economic losses are higher than the cost of the treatment. And the treatment should be done only when it's necessary and at the right time. To know this right time and the necessity, this is necessary to perform regular crop monitoring and to combine it with the good decision support system. And the crop monitoring is a weak point of the integrated pest management. Why? Because it is very time-consuming, work-consuming, and it requires highly educated staff. So what could be the solution? There's different solutions. However, in HortiQD, we are working on the element which is called precision, element of the precision agriculture. In case of the monitoring of the plants, there is no well-developed solution yet and not easily available for the agriculture, for the farmers. So the aim of this project is to develop such a system. Remote sensing technologies, this is what we are working on. They can provide real-time, high-resolution data on crop condition. The majority of the detectors, sensors are based on electromagnetic waves detection. They can involve multispectral or hyperspectral cameras. They can work in different wavelength ranges, and they can include satellite imaging. They can involve drones or other autonomous vehicles. They are quite promising non-invasive technologies for early and precise detection of the status of the crops. Spectral imaging involves capturing and processing information based on the interaction of the light with a plant. And there can be three types of interaction: reflectance, absorption, and transmission across a different range of wavelengths. And cameras detect reflectance. And these methods allow to decipher of light material interaction into wavelength-specific signals, and they can provide the information about the structural, chemical, and physiological properties of the analyzed plants. And they also offer, what is very important, the real-time insight into the plant physiological and biochemical changes. In case of diseases and pests on the plants, during the development of the disease and during the infestation of the pests on the plants, there are changes, both structural and chemical, and these changes affect the reflection of light, the amount of reflected light, and the range of wavelengths. We saw similar slide on during the previous talk. So the majority of the detectors are working in the visible range of wavelengths, near infrared and short wave infrared. We already heard that in the SWIR region we can see more than in the visible region. And why? Because the reflectance generally is much higher in the infrared than in visible range of wavelengths. So this higher reflectance, which could be observed in infrared, gives just more information which can be analyzed and transformed for the information, for example, to the farmer. What we know about, there's several studies on the changes in the plant which can be observed in the different wavelength range. What we know that there's changes during the disease or infestation of the pests. There's changes in the chlorophyll A and B. Chlorophyll degradation can be observed in the range of 680, 730 nanometers. There, for example, in the range between 500 and almost 1,000, we can see differences in anthocyanins, carotenoids, xanthophylls, and nitrogen content. It doesn't mean that these signals are spread equally in this whole range, but in this whole range, there's several bands, several wavelengths, which can be easily, which are already correlated with the changes in these compounds. And these compounds are related to the plant defense. So during the infection, plant starts to produce different products to defend, to stop the spread of pathogen inside the plant. Also polyphenols, lignin, cellulose. The degradation of these compounds are also related to the infestation of pests and to the disease development process, different disease development process. And also water. A lot of disease symptoms are correlated with changes to the water content, and we can observe the lack that, for example, the smaller absorption of peaks specific to the water. Our approach, in the HortiQD, we concentrated on 3 diseases: fire blight, apple scab, and powdery mildew, and 2 pests, mites and aphids. We started with data collection with spectrometer in the range of 900, 1900 nanometers. We collected the spectral data from different points on the leaves. For example, I would like to show you as a case study fire blight, how it was the experiment was designed. That we prepared 8 trees before inoculation. On each tree, 3 leaves were used for measurements, always the same leaves, where they were marked. On each leaf, 6 spots were measured, like you can see here on the picture. The day 0, it was so-called day 0, first measurement was done before inoculation, and just after this measurement, we inoculated the tree by cutting the shoot tip with the scissors dipped in the solution of bacteria causing fire blight, so Erwinia amylovora. And during 40 days, we measured regularly every few days the same leaves in the same spots. After this collection of this data, the data underwent the analysis. The special data sets were created. They were pre-processed. The partial least squares models were built and prepared to validation, cross-validation. Okay. What was found? That the progression of the fire blight development and mites infestation could be traced very well, almost excellently. Both for full spectra from 9 to 1900 nanometers, also even reduced spectra from 11 to 1600 nanometers. The correlation was very high, so it was really very good result. However, for the other diseases, I mean apple scab and powdery mildew, and also for aphids, it was not so easy, but not because there was a problem with data analysis or something, but we tried to do this in the winter time, when it's really not a good time for the inoculation of trees, and this experiment was repeated, but data are still analyzed, so I cannot show them today. The next approach was involving hyperspectral camera with the spectral range from 900 to 700 nanometers. And we collected the pictures of the diseased plants with normal lenses in the bigger distance and with macro lens in the shorter distance from the plant. And as well, we collected RGB images. Parallelly, we also were tagging the RGB pictures according to the scale, and the scale reflected the disease amount on the particular leaf. So this is just to show you how this is a fire blight well developed already. On the left side, you can see the RGB picture, and on the right side, the image collected by hyperspectral camera. The objects on each hyperspectral image were classified to different categories. For example, here the gray means background, green healthy part of the leaves, red diseased part of the leaf, and brown stems. Next, these data were underwent the regression analysis. The confusion matrix was created to evaluate the performance of the classification model in the machine learning. And next process, it was process of segmentation, so dividing the image in the parts of homogeneous characters. And also what was, as I mentioned before, green means healthy tissue, red means diseased tissue. And you can see that, for example, on the left side, we have day 2. On the right side, we have day 19 of the experiment, and you can see easily much more red color. So it means the disease is progressing and the symptoms could be seen by camera. For training and testing, there was set of the data were prepared as data for training, and another set for testing, and opposite. And also this set of data underwent regression analysis, and we can see that the regression coefficient was very high, over 0.97. So this means that it was possible to correlate nicely the SWIR data with the disease development. So, short summary that in the feasibility study of SWIR-based diseased pests where propagation control showed the progression of fire blight and mites very well. A little bit worse, we had a little bit worse results for apple scab and powdery mildew, but it is already repeated and in the analysis. And SWIR-based analysis allowed for the detection of infected shoots, leaves very early, even a few days after the inoculation, what is really very early. It is not possible. Just the standard way of the monitoring orchards to see if there's any fire blight. It's not any human is able to detect with human eye the disease development so early as camera was able. So based on this updated data and their analysis, the camera will be also, this information will be taken to build the camera and filter. So thank you very much for your attention.
Thank you very much, Joanna. Actually, we have a question for you, so don't leave, stay there. So the question is, what is the biggest challenge in developing a system for precise plant disease and pest recognition using machine vision system?
Thank you, but I think it's a question to the whole consortium because there are so many challenges. But from our perspective and the work which we did, it is really difficult because in the nature, this is not like we have only one disease on one tree. We can have 2 diseases and pest, and to really identify precisely what is on the tree, it is really challenging. Thank you very much.
Okay, so Thank you very much once again, Joanna. We can proceed with the next speaker, with François-Xavier Rondeau from CTIA. He's a project manager at CTIA, a French company specializing in robotics and automation. His presentation will show how robotics and spectral sensing can be combined to empower autonomous field operations for crop health monitoring. Welcome.
Thank you, Claudio. And thank you for the attendees for joining this presentation, which will deal with the synergy we can find between the robots and the high-level sensors as the hyperspectral camera is. Okay. My name is François-Xavier Rondeau, and I'm the test 3 department of the French company CTIA. And during this presentation, I will demonstrate how our autonomous tractor, whose name is Tractor, is a platform which can deliver high-level sensing capabilities. And I will highlight the support that the combination robot plus hyperspectral camera can bring to scalable, technology-driven, and sustainable agriculture practice, and particularly for the crop health monitoring. Well, I would say that nowadays, globally, agriculture must face numerous challenges, and one of them, not to tell you the first of them, is the environmental challenge. Beyond organic farming, we know that all the practice must use fewer and fewer chemical inputs to be in compliance with the environmental rules. This is made to protect our biodiversity and the food quality as well. And so we know also that the climatic change with drier period, with massive storms, with also intensive and late frost period, already impact the way of working for the farmers. And as a consequence, the farmers must go more frequently on the field to work on the field. For instance, we need to find some alternative for herbicides, and so the only effective solution today is to mechanically weed the soil, and that means that you must do this more frequently and regularly. And in parallel, if you use less chemical inputs, that means that the farmer must go also more frequently into the field to monitor the plant and to detect if a treatment is necessary, when it must be done, and also when the harvest period is the most suitable for him. That means that, in fact, the farmer must be always on the field. It's very time consuming, but at the same time, the second challenge is that less and less people work on the field. Labor is very hard to find. This is understandable because we know that it's a demanding job. Okay, driving the tractor in the field all day long is not so distractive. It's a lonely job with a few human interaction, and this is, in a way, in opposition of what the world is today, based on entertainment and activities with quick thrills. So it's very hard to hire people and young generation for this kind of job, which is very time-consuming activity. So I mean that if we take if we put ourselves in the shoes of a farmer, we would like everybody find a solution that can work 24 hours a day, and as many times it's necessary, on demand, on when I need it. Okay. This is in this context that some robot solution have emerged to help the farmers. And tractor from CTR is an autonomous electric tractor which is born for this purpose. In fact, tractor is a tireless worker. Thanks to the hybrid energy, you have some wheels which are driven by electric motor, and you have also a thermic generator we can reload. And that means that this solution can work 24 hours a day, 7 days a week. So it's a solution for lack of people. At the same time, it was designed for multi-cultivation, and this is particularly well sized for horticulture. I mean, in market gardening, vineyard, and orchards, of course. Of course, when you talk about autonomous tractor, autonomous vehicle, you have to take care about the safety for sure, because there is always people working around. And so tractor includes some advanced functions to detect obstacle and manage all the safety all around. And the last but not least characteristic is this is a connected device, and it will be really important for the next slide. I will explain to you into the HortiQD project. Well, the robots, in fact, define a new tool concept. This is a tool to use the other tools. You have a few images and short video there. You can see some application. On the top left, it is a ridging operation in vineyards. We have also some sowing into greenhouses, or bed preparation in outside market gardening, and even some harvest operation into orchards. And that means that we have many cultivation and application. You understand that tractor used conventional tools by the farmers. Tractor is able to take and load all those tools, either they are hydraulic, electric, or only mechanics. But this is traditional. And at the end, the farmer can use tractor as is traditional tractor, but with the advantage that this is always available. Okay. But the next step is to think about other tools. And what about a smart tool, which could be make some action non-systematic? I mean, when we talk about mechanical tools, it cannot be selective. Okay, it's systematic. But if you can find a tool which can define if I have to keep this plant, treat this one, or destroy this one, it would be very efficient for farmer. So imagine also tools which is able to give live information, or maybe postpone one with a global overview of your orchard or your field. It will be very interesting for the farmers. Okay, because it will be a large support for decision making. Okay. Of course, to do that, these tools must collect a lot of data. Okay, to give recommendation and so on. And when we talk about large amount of data, we think about artificial intelligence, because we can imagine also deep learning. And if we can imagine such a tool, it would be very interesting to add it on the tractor. But actually, this is exactly what the HortiQD tool is, because this is made to detect the disease, or the growing disease, or if it's attacked by a parasite. So it gives solution to give maybe only alert to an alert to the farmer, but it's already an interesting step, and we can also imagine some large analysis later. So this is clearly in the scope of the decision support, and collecting large amount of data and using advanced processing tool, as I'm going to describe later. Well, I suppose you understand that now Tractor is not only a carrier of traditional tools, but it's also a kind of junction node between the crop and the advanced processing tool. This is a bridge between all those functionality, and this is the functionality that all the contributors of this project are bringing to the machine. I propose you an animatic diagram to well understood. We can imagine a use case. I mean, a farmer into an orchard has to make a control on the trees because he wants to know if there is some disease, or he wants to predict the most suitable period for the harvest. It's very time consuming for the farmer, okay? Because if he has to control every tree, it's awful. Even if he shares this task with other people, we can suspect that there is different way of diagnosis from the people. So it's not really objective. But now, if we give the mission to, sorry for that, I suppose I can use, yes. If I give the mission to Tractor, passing through every tree, it will a game changing, okay? Of course, sometimes we can control, we can control the leaves or maybe the fruits, many of situation, but in both of them, we can detect some visible things and non-visible one, okay? Because the disease is just started or the parasite is very small and included into the fruit. And this is why the HortiQD camera is very helpful, because it will take a lot of pictures and be able to give information, including the embedded artificial intelligence, to give a first level of information. All those data will be then transferred to Tractor system. Tractor will be able to enrich those data with additional data. One of them is obviously the GPS localization to know this tree is okay, where is it, okay? We can imagine also weather condition and so on, temperature, moisture, and so on. And then Tractor will send those data to the web platform, which will then take the leads to make some reports, to make some analysis, and even support for decision. Okay. So this is the full workflow we can find with this situation, this project. And I hope you understand why I say that the robots is the bridge between the crop and the advanced tools in the web platform. So at the end, combining the robots and the high-level sensor as the spectral camera give a real helpful tool for the farmer. This is a high value-added solution, of course. If the farmer is able to take a decision with objective information and to select the good treatment at the good moment, it's really helpful, and it's clearly in line with the European Green Deal. That means that I will complete that this method is also scalable. I mean, it's ready to welcome other technology, other innovation, and we can imagine other things for the future. And as all of this is made to optimize the way the crop are managed. This is a sustainable method. at the end, the farmer with this tool can improve its productivity and also gain serenity. Okay. So that's why, once again, robots plus eye sensing technology as hyperspectral camera here can the farmer meet the challenge from today, but also prepare the one for tomorrow. Okay. Thank you for your attention.
Thank you, François Sallier.
We have a question for you too.
Yes. Okay.
And so you described the data flow coming from the hyperspectral camera, passing through Tector platform and uploaded to the cloud to be post-treated by high-level tools.
Yeah.
But could we imagine that the loop being closed with downstream data from the cloud, results of calculation or decision made off-site, which would be transmitted back to the robot to perform specific and dedicated actions?
Okay. Well, I would say for the moment, the HortiQD project has been defined to give data to farmers. I mean, to have some recommendation, some prediction for the disease. The human is always in the loop to take the decision, final decision. This is the situation now, but it's not forbidden to imagine the future. Because with collecting large data, as the system will learn and learn more and more. The artificial intelligence with the deep learning will try to be more and more efficient. And imagine that we can also include a part of the farmer experience in this situation. We can easily imagine close the loop because the technology is already ready to go back to the tractor and pilot some actuators to maybe cut a leaf or spray a dedicated treatment on an apple, something like that. The technology is almost ready for that. Okay, but I think the system must learn and learn more for the moment. I would say also that except this deep learning necessity, there is also a barrier that means that people must accept the automatization of everything. Okay, but if I can make a comparison between the autonomous car, we know it's not ready today, but we know that in the future, in a mid or long term, it will be prevail. So I can imagine the same thing for this kind of solution. Maybe not tomorrow, maybe not the day after, but maybe next week. So this is the future, I think. Yeah.
Okay. Thank you very much. So we can proceed with the last speaker of today, with Stefano Paolini from Resi. Stefano is pre-sale engineer at Resi, where he designs proposals for European research projects. And today he'll show us how smart data platforms can turn sensor readings into meaningful insights for farmers and researchers. So welcome, Stefano. Give me just a second to share your presentation.
Okay. Hello, everyone. Thank you for those who are attending online, and thank you to Claudio for the introduction. So I will skip this slide and get to the point. So as we already seen today, agritech and agriculture 4.0 are terms which define the new trend in agriculture, where massive amount of data are collected from the fields and from the orchard, directly from sensors or from mechanical instruments. So from sensor, we can get GPS positioning, humidity, wind, rain information, temperature, And from the mechanical aids to the farmer, we can get the quantity of harvested goods. In HortiQD project, what type of data are we collecting? We are collecting for sure, as also Francois highlighted, GPS positioning, temperature, and pictures, images from RGB cameras and infrared cameras. All of this information are collected and stored into a system which has been designed by Resi, and it's been implemented. It's already at a good stage. And this system shall contain all this information and be able to present them to the end user. What is the travel that the information makes from the field to the DCCS, the data collection and correlation system? This is the name of the solution that we provided. Here we have the tractor in the orchard, okay? And we collect from the tractor directly through the internet connection, or also by an offline method of collecting data. We collect the data, and through a dedicated interface, we store them into the database we designed. Since the infrared camera, which is designed and created in this project, can be also used handheld by a human operator, the data can come directly from the camera, and in particular from the embedded system, which is a machine learning system that processes the infrared images and can detect the presence of a disease on a tree. This external module can connect to the DCCS system too, through a dedicated interface, a connector. And this system is also able and is ready to accept external data, because the more data we have, the more rich information we can provide to the end user. So if we have, let's say, historical weather bulletin for the area where the orchard is located, we can import them through the system via a dedicated interface that which can be developed. Okay. With all of this information, multiple type of analysis can be performed. It can be big data analysis, correlation through different parameters, or data can be also be provided to external data modules. In any case, the result will be shown through a web-based user interface, which can provide graphical tools, graphical representation that we will see in the next slide. The system is able to be configured to set thresholds. That is, if we want to be notified by the system that, for example, a temperature is rising above a certain level, or the number of trees which are affected by a specific disease is over a certain number, we can set a threshold and get a notification alarm on our, for example, mobile phone or in our email, or on the screen, of course. And the system is also ready for the degree of automation that Francois explained to us in his the last part of his speech. Therefore, if we do have available an automation external control room, the system can provide through a dedicated interface a signal if something needs an attention. For example, if a tree must be sprayed with a specific substance, the system could provide a signal to the tractor or to another robot to start the treatment on that specific plant. So let's say the system is future-proof. If additional treatment processing of the data is needed, external analysis module based on deep learning, statistical techniques, or other types of data processing can be integrated into the system, providing that the data is taken out of the database, passed to the external data analysis module, and then returned with the results returned to the database again. At the moment, the DCCS features are shown in these slides. I will go through them shortly. You can see on the left side some preliminary images from the web interface. So the system can provide the representation on a graphical map of the data collected from the orchard. We have a user management feature, that is, we can it is possible to configure different users with different access rights to the data that will have different visualization of such data for each user. Different working areas, that is, if a farmer has different charts, multiple fields where he goes to work, he can define such working areas into the system, and when the data is collected in each field, it will be represented on the specific field where it belongs. The system also has a manual upload interface in case the farmer is collecting data with an offline method. Okay, so if it has the data on a memory card, he can go to his computer and upload the data from the memory card. And what else? Threshold setting, we already said for the previous slide. And of course, we have API gateways, that is, application programming interfaces that are the interfaces to collect data from external sources and provide data to those systems who require them. It is possible to perform correlation across multiple parameters in order to highlight what are the meanings hidden in such a large amount of data which is stored into the system. Okay, so if we can think about the DCCS and we can think about its application, we must take into account that the objective of the agriculture today is to use, as my colleagues already told us, is to use less and less pesticides and chemical substances in order to get more crop from the fields. This system helps the farmers towards this goal because it will pinpoint the ill plants that needs to be treated in the orchard. The system, it is also, let's say, a multi-purpose tool. It's like a Swiss Army knife. It can be enriched with the different analysis mechanism logics. So if we want to investigate if two parameters, if two measured items are correlated somehow between them, we can perform correlation between large amount of data and try to understand if such correlation exists. And applying mathematical models, we can also try to highlight what correlation, what type of correlation exists between parameters. In automated farm environments, which are coming on the horizon, let's say, maybe it's not the future of the agriculture, but are somehow taking some parts of the market. This type of solution could be applied to provide the information to the robots and the automated farming tools used there. Okay, and I think this is most of the information I wanted to deliver to you today.
Thank you.
Thank you.
Thank you, Stefano. We have a question for you. I think you may even answer yes or no, simply, but let's see. Do you think this software can be useful in hydroponic vertical farming too?
This is not the question. It's not the answer, not just yes. This type of software could be definitely used there because the hydroponic farming systems usually already implement somehow the closed automation loop which Francois depicted in his speech. And we know that there are already some farms, fully automated farms, and these farms are have a very large set of sensors in their infrastructure. So the collection of large quantities of data from the sensors and the subsequent processing and let's say the calculation of suggested actions that can be performed automatically or by the input of a human operator is greatly facilitated by the usage of such software. Thank you.
Okay, this was the last presentation for today, but stay there because now it's your turn, and I'm talking to the audience because right now we are going to learn something more about you. So you can give us also your inputs and feedbacks on what you listened today. And so you can give us also inputs for discussion. So you can take your smartphones and with your camera check the QR code you see here, or you can go to menti.com and enter the code, and you will be able to enter in our questionnaire right now and our feedback, let's say feedback form. So I'll leave it this here for a minute. In the meantime, I invite here with me Jonathan Steckel. Jonathan is Director of Advanced Technology in Imaging at ST Microelectronics. So you can come here, John. We will be looking at the answers. So let's just wait another second here, and we will proceed with the first question. First question is very easy. So the first question is, what is your area of expertise? Just to know more about you. So as we can see live your answers. Let's wait for the others to join. Okay.
So it's like pre-selected categories?
Yes.
Okay.
But we also left the space for others.
Okay, yeah.
So as you can see, we have already 3 experts in sensor and spectroscopy, an industrial automation expert. So waiting for the others. As soon we get to 11, oh, we have 12. Let's wait. That was not a tough question. So we have 3 of you still. We're still waiting for the 3 of you, but I think we can.
Don't be shy.
Don't be shy. Yes.
Embrace this new technology, this platform.
Oh, I think if they're shy, the last 3 I think we can go on. But at least we have an overview of our audience now.
That's good, yeah.
So let's go with the next question.
Got a lot of sensor people.
Yeah. So what is the most important benefit you expect from solutions developed within the HortiQD project? You had the chance to discover something more about HortiQD. So for example, quantum dot enabled with cameras and other aspects. So what is the most important benefit you expect from solutions developed within HortiQD project?
Also multi-choice.
This is a tougher one, so we have to wait. So
it pops up as a,
yes,
you
so
can't choose from menu.
exactly. So we have,
have to write something.
already some inputs. So we have a chip system for automatic monitoring of orchard. We can also discuss this.
Yeah,
I
cheap
think,
is a very relative term.
yeah, also a cost-effective solution.
Cost effective. Yeah.
Yes.
We can make super cheap sensors, but in the end, that tractor and the rest of the system is
Yeah.
probably going to be
Yeah.
quite expensive.
But I think we can also give some word to our consortium about this. Let me take the microphone and. So if some of our consortium partners want to say something about these inputs, like a chip system for automatic monitoring of orchards and cost-effective solutions, if you think it will be feasible and easy to achieve. Is it right?
Yeah. Cost.
Yes, we have in-field applications of hyperspectral camera.
Yeah. Yeah, like real use.
I would like to take opportunity to give a comment to the question which Francois was answering. That was more or less about whether that is possible or will be possible somehow that the instant reverse information from the cloud could make the machine taking some specific action. Well, in my opinion, that will be possible, but will depend on our ability to reduce the amount of data which has to be passed to the cloud and back, because that means the time. So the machine, the autonomous vehicle cannot stay in the place waiting for the answer, then move a little bit, make the measurements, and again stay at the place waiting for the answer. It has to be much quicker. But if we achieve that, then it will be possible.
The end, if it's an autonomous system that can operate 24/7, maybe it can just sit there and
yeah, all you have to do will be supply more fuel, for example, or recharge, fill in the tanks with some, I don't know, liquids for precision spraying and things like that.
Right.
Yeah, thanks.
We also have another input for challenges in outdoor conditions. So I don't know who can help us.
Just Claudio, please. I would just make another additional comment, because we can also imagine a first scan, a first mission to scan the orchard, let the system process, and a second mission to make the adjustment on. So twice, but as we can work 24/7, it's something we can imagine. Probably, yeah. It will be
cost.
sure.
We have another input for real-time processing of hyperspectral camera.
Interesting. Yeah.
I think we can go on. Do you agree? Yes. Okay, next question. So what is the biggest barrier to adopting these technologies in your operations?
Weren't many people online that were farmers, so this might be tough.
Yeah. Let's see. They give us some inputs. Obviously,
Okay, cost,
it's always the money.
Yeah, exactly. We just have to convince the the government to subsidize the cost of the entire system.
Yeah. It was predictable, I think.
Yeah.
The answer.
Yeah.
Yes, but there are also technical integration challenges. There's also a proper training maybe that must be done.
Yeah.
And also regulatory compliance. Yes. Oh, compute capacity. So from if the consortium want to spend some word about this. Joanna? Oh, no.
Yeah.
Also the data volume, yes.
Yeah. Makes sense, yeah. I mean, over time, the compute capacity will get faster and faster and better and better.
Okay.
And could become more selective.
Also technology, maturity, and reliability.
Yeah, that's true. Maturity, reliability.
This is actually a good input for discussion also for our consortium. So, what do you think is the state of the art about technology, maturity, or reliability? We can, Stefano, do you want to?
Yes, in my experience, the computing capacity and the data volume are not a limiting factor, let's say, when designing such a system. It is true what Pavel was saying. Sorry. It is true what Pavel was saying. The speed of data transmission to the orchard and back would be important in case of high data volume. This can be overcome by data compression and 5G coverage of the area. The maturity of technology from information technology point of view is not a point, because the technology is mature, and the cost, let's say, is reasonable on my point of view. Thank you.
Okay, I think, Jonathan, we can go on.
Sure.
Yeah.
Unless someone wanted to mention anything about reliability.
No. Oh, the next question is, how likely are you to pilot or implement HortiQD solutions after validation, obviously? So we have some answers like not likely, slightly likely, neutral, somewhat likely, likely, and very likely, obviously. So let's wait for the inputs. Yeah, so someone just said, yeah, maybe.
Yeah, I think so, yeah. It would be like a full solution of the output of the program. I guess would be to have that fully functioning tractor. Yeah. With a good illumination source.
Okay, so slightly likely. Likely and very likely, so.
Okay, getting a mix.
Yes. It depends also on what cost. The cost. Yeah. No. Mostly on what is your needs.
Yeah, exactly.
So,
yeah. I don't know if in the audience we have anyone that's really a farmer.
I don't know.
Are there any farmers in the audience?
How?
I think we did have any.
No.
I didn't see that in the beginning.
I don't remember actually, but I think
sensor guys.
Sensor people. Sensor enthusiasts.
Yeah.
Okay. So yes. So we may say that we're in the middle between somewhat likely and likely. So it's an interesting, obviously, solution, and yes, after validation, it may be a useful solution. So let's go on with the next question. So how would you like to be involved in the rest of the HortiQD project if you want to be part of our process? So there are three options. So you can receive regular updates, you can be invited to future events, and provide feedback on developments. Okay, and we will have plenty of future events because we are planning more webinars, we are planning more workshops, and we are also planning a school for PhD and students. So there's plenty of events ahead.
Yeah, absolutely.
So yes, you want to be invited to the next events, and we will do. Yeah, very likely.
Great.
Yes. And also receive regular updates. So about this, we are working on the newsletter, and this also gives me the opportunity to tell you that obviously HortiQD project is on social media, on LinkedIn, on Facebook, and we also have obviously our website, so you can follow us and you will be up to date with all the operations that are ongoing in the project.
Providing feedback on developments, that's nice too.
Yes.
It's always good to get input and ideas.
Yes. But if you are invited to events,
Yeah, then
there
they can
may
provide.
be space for that. Okay. So another question: do you have any suggestions for the consortium? This is freely, you can write freely, and we will keep it in next to our hearts.
That's right.
Thank you very much. If you want to share something about this. So you learn more about the project and what we are developing. So if you have any suggestion for us, that could help us to reach, I don't know what, but
Yeah.
new achievements for sure.
They want to have a drawing at the end of the program for a free tractor.
Yeah. Oh, obviously someone said no suggestion now. Looking forward to learning about the results, and that's comprehensible.
Good.
Yeah.
Absolutely.
It's
Yeah.
obvious.
Makes sense.
We also have detection of disease before symptom appears. Would be interesting. I don't know if Joanna, you want to say something about this. Do you think? Do you think it would be possible?
We are going in this direction. This is also what I mentioned during my talk, that, for example, in case of fire blight, sphere imaging was able to see the symptoms before it was possible to see by the human eye.
Okay. So yes, it's possible.
Yeah. It seems like multispectral SWIR image sensing is definitely viable for that.
Yeah.
And it could be in lots of different form factors, right? It doesn't necessarily have to be mounted to a tractor, but just the fact that, we're developing a solution that could be low cost and competitive for multispectral image sensing in the SWIR for this type of application would be viable for a lot of different people to use in different ways.
Yeah.
Foster detector development.
Yes, we also have the foster the detector development. Yes, obviously.
It's a good community.
Yes.
The QD technology community.
They know what they want.
Strong community. Yeah.
They know what they want. They know what they need.
Yeah.
Okay. So if there is no other input, I think we can go on in 5 seconds. 4, 3. Okay. So that was all. Thank you very much for answering our questions. And we will be in contact then, since you wanted to know more about this. And so I think it's all from our side. I don't know if our coordinator wants to say something more. So we want to thank you all for joining us today for this workshop. As I was saying, there will be more events in the future, so stay tuned. You can get to know about them on the website and on our social media channels. So I don't know if the consortium someone from the consortium want to say something more about the inputs we received. Are we clean? Okay, we are okay with that. So thank you very much, and we hope to see you in the next event of HortiQD project. Thank you very much. Goodbye.